here is a theorem that we have to prove. The theorem is if the function f is differentiable at x equals to a, then the function f is continuous at x equals to a. So this type of statement is a one-way implication. So the implication is differentiability implies continuity. You can use this symbol, this one-way arrow, that means implies. This is called one-way implication. Differentiability implies continuity. The reason I call this one way is because differentiability implies continuity. This is a one-way arrow, right? From one step to another step, but you cannot go back. That means if you know continuity, that doesn't guarantee differentiability. Once again, this is a one-way implication. Differentiability implies continuity, but you cannot go back. You cannot say continuity implies differentiability. All right, so make it simple. A implies B. That means if A is true, then B is true. So let's give a proof to this theorem. So we already know that f is differentiable at a, so the differentiability is f prime of a, that is equals to limit as x goes to a, we have f of x minus f of a divided by x minus a. We talked about this when we were learning average velocity, and the graph is like that. We have a curve, we have a point A, and then we have another point X. I draw a straight line between A and X, and I want to use the slope equals to rise over run to find the slope of this straight line. So that's why I use y2 minus y1 divided by x2 minus x1. Okay, so what we want to prove is we want to show that actually I'm going to erase this line because I need to state what we wanted to show. So we want to show, that we want to show continuity. So let's say we want to show continuity. So what is that mean? That means as limit as x approaches to a, f of x is equals to f of a. What does that mean? So f of a is a solid point, and then as x approaches to a from either side, the left limit and the right limit stop at the same point, so you can sketch the entire curve without picking up your pencil. So that includes x approaches to a from the left, also x approaches to a from the right. And then the hardest part of this proof is you have to know what you start with. So in this proof, we are going to start with limit as x approaches to a, we have f of x minus f of a. And then the next step is even more complicated. So this is x approaches to a. I'm going to copy this and save some space for myself. I'm going to copy this. I'm going to take a quantity times f of x minus f of a. So f of x minus f of a. And then what's the extra quantity? The extra quantity is, I'm going to do that in red, is x minus a, and then x minus a. So if I do this, I just multiply f of x minus f of a with x minus a divided by itself. So that doesn't change the equation, right? That doesn't change anything. And then you have to split it up to two limits. So that is equals to limit as x approaches to a. We have x minus a. This is the first limit. So since this is a multiply, then we have a multiply limit as x approaches to a, and then we have f of x minus f of a divided by x minus a. This is what we already know. That is what is given. So in case you ask me, hey, you start with one limit and then you break that up into two limits, how's that work? So here is how that works. Let me use give you a better contrast. So here is I use a product law. So product law, let's just put it right here. Product law is simple. So let's say you have limit x approaches to 10, 2x times 3x. You plug in the 10 to find out what it is, right? 20 times 30. That is the same thing as limit as x approaches to 10 to x, and then you multiply limit as x approaches to 10 to x, same thing. Plug in, evaluate is the same thing as splitting up into two factors, and then plug in, and then you evaluate, and then you multiply the result. Okay, and then back to our business. So we have to specify that this is given, right? So this is equals to f prime of a, f prime of a, and then this is given. Is given because we started at differentiability. We already know that f is differentiable at x equals to a. So that means f prime of a exists. So f prime of a exists. And then how about the other limit? So the other limit, once you plug in a, so you basically just get a 0, right? And then you get a 0 multiply f prime of a, 0 times f prime of a, that is just equals to 0. Okay, so that is just equals to 0. And then what is the conclusion? The conclusion is therefore, so, and then we draw a conclusion, therefore, limit as x approaches to a, f of x minus f of a, that is what we started with. If you look at the first line, so right over here, that is what we start with. What is that equal to? That is equals to 0, right? And then that is equals to 0, and then basically this is, and then of course I want to draw a statement and then say what that means. So that means we know that limit as x approaches to a, f of x equals to f of a, which means f of x is continuous at x equals to a. So this is the end of the proof. So this is done. And then what else do I wanted to say? You might ask me, hey, how do you know that f of x is equals to f of a? So here is how. So in case you ask me, hey, how do you why do you say they are equal? You just got a 0, and then somehow now you say they are equal. I don't get it. So here is why. So you have actually I will just do it as a side note. So this is a limit as x approaches to a. We have f of x equals to f of a, right? In case you ask me how. So how? So we started at this line, x approaches to a, and then we have f of x minus f of a, that is equals to 0. And then we can break this down into two limits. So this is one limit. We can break this down to limit as x approaches to a, f of x, and then minus limit x approaches to a, and then f of a, that is equals to 0. So in case you don't know what I am talking about, so let's say limit as x approaches to 10, 2x minus x is the same thing as limit as x approaches to 10, 2x minus limit as x approaches to 10, x. You can just split that up into two limits. So once x goes to a, so this is just an fa, right? So this is just an f of a, and then since they are equal to 0, you can add f of a on both sides. So and then you will get x approaches to a, and then f of x, that is equals to f of a. So that's how I got it. And then I have more to say regarding this theorem. The first thing that I want to say is the contrapositive. Contrapositive is true. So let's put this down. The contrapositive. So contrapositive is true. What is the contrapositive mean? So let's go back to the theorem. The theorem says f is differentiable, then f is continuous. The contrapositive is if f is not continuous at x equals to a, then f is not differentiable at x equals to a. That's the contrapositive. And then one more I have to say is the converse is false. The converse is false. Why? So the correct answer is, so we just said that differentiability implies continuity, but continuity does not imply differentiability. You cannot go backward. We said differentiability implies continuity. That is a one-way implication. But continuity does not imply differentiability. So one typical example is y equals to absolute value of x. And then do you remember this graph? We have this graph, right? And then there is a sharp point and x equals to 0. So this is continuous at x equals to 0, but not differentiable at x equals to 0 due to a sharp point, because 0, 0 is a sharp point. So that's why I said continuity does not guarantee differentiability, but the theorem is said differentiability implies continuity. Differentiability implies continuity. The other way is not true, which is continuity doesn't imply differentiability. All right, so that is the end of this video. If you like it, give me a like, and I will see you all in the next lesson. Signing out.